Okay, in this video I'm going to talk about a really important behavior of the undrained strength of clay, and it's normalization of the undrained strength with vertical effective stress, or alternatively P prime, and OCR. So if we know P prime and OCR and we know the position of the normal consolidation line and critical state line, we can actually calculate the shear strength based on those properties. So I wanted to show you how, and then this has implications for how we evaluate the strength of clay in the field. Like, for example, let's say we're building a levee, and the levee is on a soft clay deposit that's going to consolidate. Well, what will happen is over time the clay will become stronger beneath the levee because the effective stress is increasing as it consolidates, whereas the clay will be weaker in the free field where there's not that levee on top of there. If we didn't have these strength normalization concepts, we wouldn't really know how to project the increase in strength over time of that clay. So this is really an important concept, very fundamental for soil mechanics. Okay, so what we'll do is start just with two of the stress paths. We're going to not have the two stress paths that are versus deviatoric strain, epsilon Q. All we need are these two right here. So on the bottom, we have E, ln P prime. And that one's really busy, a lot of annotations there. And then on the top, we have Q P prime. So this bottom one is actually the more important one for strength normalization. I'll spend most of my time talking about it. So what we'll do right now is start with a normally consolidated condition. So we're starting right on that point. And then we're going to move to the left and reach the critical state line through an undrained stress path. So here, this line is the normal consolidation line. Its slope is lambda. Here's the critical state line. Its slope is also lambda. And what we'll do is write equations for these 2 points. We know the starting point and we know the ending point. Okay, so the starting point, the void ratio is equal to E naught NCL, which is the intercept up here when ln of P prime is equal to 0, right? So that's the intercept of the NCL. And then minus lambda times ln of PC prime. So we're going from this point down to that point along this slope lambda. And notice that we have ln of P prime is 0 here, and this is ln of PC prime, or we'll call it the consolidation stress. It's the mean effective stress under which the soil is consolidated. All right, similarly, we can write an equation for this other point at failure on the critical state line. It's E is equal to E naught CSL minus lambda times ln of P prime F, where P prime F is the mean effective stress at failure. All right, now, because the stress path is undrained, E doesn't change during loading, which means that these two expressions have to be equal to each other, right? So we set them equal to each other here. And then we solve for P prime F here, right? Just doing some algebra. So pretty straightforward. And then what we can do is expand out this exponential function, right? The exponential of two terms added together is equal to the exponential of one multiplied by the exponential of the other. And then, of course, the exponential of the natural log of PC prime is just PC prime itself. So we can pull it out right there. And we get that P prime F is equal to PC prime exponential of E naught CSL minus E naught NCL over lambda. All right, and then what we do is go from this point up here and figure out how much is Q at failure. In fact, let me write in that term right there, Q at failure. Use my blue pen just to be clear, consistent. Okay, Q at failure is the deviatoric stress invariant when the soil is failing, and it's easy enough to get it. It's just equal to MC times P prime F, right? So we've solved for P prime F. Now we just multiply it there and we get this. Okay, and then what we can do is notice that Q at failure, which is basically the strength of the material, is linearly proportional to P prime C, the consolidation stress. Well, that's really useful because we know the consolidation stress, right? We know it and we can easily get it. And all of these terms over here are basically material constants, right? So we get QF over P prime C is equal to this constant, MC exponential of, those terms in there. And this is for, remember, this is for OCR equals 1. We started on the normal consolidation line, so we haven't gotten to the effect of over-consolidation yet. But what we can do is say that this stress ratio, this strength ratio, QF over P prime C, is constant for OCR equals 1, which is a normally consolidated condition. So this ratio right here is the normally consolidated undrained strength ratio, and we treat that as being a material constant. Okay, we can do some laboratory tests and measure this material constant for a clay. The only condition being that the normal consolidation line and critical state line have to be straight lines, and they have to be parallel to each other. Okay. Now let's go and talk about the influence of overconsolidation ratio. So what we'll do now, we've consolidated to some maximum pass pressure, we'll call it P naught prime, and then we unload along the unload-reload line to a new pre-consolidation pressure, ln P prime C, right? So P prime C is the current consolidation pressure that the soil is experiencing. And so we've gone down that lambda line to get to the maximum pass pressure, and then we've unloaded along another line, kappa, and kappa is linearly proportional to C sub r. And so we're starting at this point. Now this is dense of critical state, right? We've moved to the left of the critical state line. We know that the stress path is going to be initially a little bit contractive before becoming dilative and reaching failure on the critical state line. So if we come up here, this is our stress path. And notice that I haven't drawn these lining up anymore, right? If you were to draw a vertical line up here, it wouldn't match. This one is kind of close, but not really. Okay, the reason is this is natural log of P prime, and this one is P prime. So the axes don't perfectly align anymore. It's one of the downsides of doing this for clay, because we know that these are straight lines in ln P prime space, so we tend to draw them that way, but then they don't perfectly line up. But anyway, that's okay. So now we have P naught being the maximum pass pressure, PC prime is the consolidation stress, and OCR then is equal to P naught prime over PC prime, which means that P naught prime is OCR times PC prime. And what we're trying to do now is figure out what is ln of P prime at failure given ln of P prime C and OCR, right? If we know those two things, we can figure out P prime at failure, and then we can come up here and figure out the value of Q at failure. So let me again draw these down so that it's clear. This one is P prime at failure, and then Q at failure is here. We do this the same way. We write out equations for void ratio. The critical state void ratio is the same, right? It's just E naught CSL minus lambda times P prime F, so you see that term there. The one on the at the current condition is a little bit more complicated. So first we have to go from this point to this point like we did before, and that's this term right here, E naught NCL minus lambda times ln of P naught prime. But then we have to add a little bit of void ratio because when we unload, the void ratio increases along the kappa line. So we have this plus kappa ln of P naught prime minus ln of PC prime. All right, so then we make a substitution. We want to get rid of the P naught prime because we just want to know what's the current consolidation stress, right? So we want to make a substitution for OCR. So we make this substitution, P naught prime is equal to OCR, PC prime. And then we note that ln of P naught, lambda ln of P naught prime is then equal to lambda ln of PC prime plus lambda ln of OCR, right? And so we know this term now in terms of just PC prime and OCR. And then we also note that ln of P naught prime minus ln of PC prime, that's equal to the ln of OCR. That's this term inside there in the kappa. So after making the substitution, we end up with this equation, and then we can solve for PF prime, and we get this one right here, right? It's the same as what we got before, except we have this new term right there in the middle, lambda minus kappa over lambda times the ln of OCR. So then if we do our multiplication, notice that this term, well, first of all, you'd have the exponential of this term times the exponential of that term times the exponential of that term. The exponential of this one is equal to OCR raised to the lambda minus kappa over lambda. So we end up with a simple expression for PF prime right there. And this initial term was equal to the normally consolidated strength ratio, right? So if we go back up, we see that this equation reappears down here, right? So we've got this one, right? That's equal to QF over PC prime times NC, or sorry, QF over PC prime NC. And you can think of this as a material constant. Then we have an OCR raised to the lambda minus kappa over lambda term. And so you end up with a pretty simple expression now for accounting for the effective overconsolidation ratio. OCR tends to increase the shear strength, right? If you're at a particular mean effective stress, but you're overconsolidated, that means the void ratio is lower, so the soil is stronger. And now we can account for that using these equations. Okay, now I wanted to go through this just to prove to you that the undrained shear strength of clay normalizes with vertical effective stress and overconsolidation ratio in a certain way. In reality, we don't go and measure MC and measure E naught CSL, E naught NCL, and lambda and kappa separately, right? That's a lot of different parameters that we would have to measure independently. Since all of these are constant, what we can do is lump them together into a new constant and just go and measure that material constant directly. Okay, so we have the theory behind it. Now we know that we're justified in treating them as a constant. We can do that. The other thing is that we usually work in terms of undrained strength instead of the deviatoric shear stress invariant at failure. And we usually work in terms of vertical effective stress, sigma VC prime. That's the vertical consolidation stress, instead of PC prime, right? We don't often calculate K naught, or you could estimate it easy enough, but just for convenience, we tend to work in terms of SU and sigma VC prime instead. Lambda minus kappa over lambda is a constant, so we can lump it together, and we'll call it M. And so we end up with a form of the equation that's really simple, right? SU over sigma VC prime, which is just the ratio of the undrained strength to the vertical consolidation stress for a soil in its current condition, or even in some future consolidation condition for that matter, is equal to this constant, SU over sigma VC prime NC, times overconsolidation ratio raised to the M power. So all we need to do is get these two constants now. And we run consolidated undrained strength tests to get them a lot of the time. All right, now, one thing we need to remember is that we've assumed that the NCL and CSL were parallel straight lines in E, L, and P prime space. That's how we got the equation. That's how we proved that strength normalizes with vertical effective stress and OCR. If this is not the case, right, then SU over sigma VC prime NC is not a constant. So there's no such constant for sand, right, because sand doesn't have a straight line, critical state line in E, L, and P prime space. So we say that undrained strength does not normalize with sigma VC prime. So another thing we often will do is run tests on a soil that's normally consolidated, right, OCR equals 1, and we'll run the tests at different consolidation stresses in the lab. So we'll consolidate to maybe a small-ish pressure, a medium pressure, and a high pressure, all of which are bigger than the maximum pass pressure for the soil in the field. And if that plots along a straight line, then the shear strength normalizes, and we're justified in assuming that this is a constant, right? What you would find for clay is that it's a straight line. For sand, it's not. It's going to curve. It's not going to normalize. So it's a little bit trickier with sand. Now, once we've determined that a particular soil does normalize with effective stress, what we can do now is vary the overconsolidation ratio too. And then, usually we'll do a couple of points at each OCR and then try and curve fit a regression through the data points to get the M constant and the SU over sigma VC prime NC constant, right? Those just become constants of regression. All right, now if we don't measure these materials, a lot of the time people use presumptive values for them because they've been measured for a lot of different soils. And it's not common that we're going to do consolidated undrained strength testing for clays for just kind of a typical project. That might be reserved for a really big project, expensive, big budget. So let's look at presumed values of SU over sigma VC prime in C and M. And these will come from Chuck Ladd's Terzaghi lecture in 1991. Kind of a really important paper where he summarizes a testing approach that takes advantage of strength normalization concepts using consolidated undrained strength tests to get these constants. And what he found after doing a whole bunch of different tests is for different soil types, they tend to be fairly consistent. So SU over sigma VC prime in C is approximately 0.2 to 0.25 for a direct simple shear stress path. A little bit higher for triaxial compression, maybe about 0.3 to 0.35 for triaxial compression. All right, and there's a reason why clay tends to be stronger in triaxial compression than in direct simple shear. As you recall, the particles are like flat plates, and they tend to orient themselves with the preferred particle orientation being horizontal. So the plates don't tend to go vertical, they're this way. When you do simple shear, you're simply sliding those plates past each other, which happens fairly easily. When you do triaxial compression, you're kind of pushing them against each other, so the strength is higher. So it's really a fabric anisotropy that's causing the strengths to be different. A lot of the time, we just use the direct simple shear strength because it tends to be fairly representative of a lot of field conditions, right? So if you're building a circular tank on top of soil, it's going to push down on it, and a triaxial compression stress path might be good. If you're looking at a slope stability problem, direct simple shear is pretty good. Even a basic bearing capacity problem, right? You're going to have part of it that's like triaxial compression, part of it that's like extension, and part of it that's like shear. Kind of it averages out to be like a direct simple shear stress path. So the 0.22 is a really common number that people use because it's kind of in the range there. Okay, and then that M value is often taken to be 0.8. M is approximately 0.8. So, if you don't know anything, if you don't have lab test data, and you can't reasonably get lab test data for a particular site, you can make an assumption that SU over sigma VC prime in C is 0.22 and M is 0.8, and you can already calculate the strength in the field if you also know something about overconsolidation ratio. Sometimes we do know OCR just from stress history. If the clay has been deposited underwater and there's never been anything loading it in the past, it's normally consolidated. So you'd be able to then estimate its strength profile without even going and pushing a cone or doing anything in the field. So this strength normalization concept is really powerful, very fundamental. It's a good thing to keep in mind when you're interpreting the strength of fine-grained soils like clays, silts, maybe even organic soils.